Okay, so my name is Andres, and I'm going to be talking about the thermocouple for the last time today. Okay, so basically our whole experiment was just trying to find the thermal time constant of our K-type thermocouple. So firstly, I wanted to address what it is. The thermal time constant is just the time that it takes our thermocouple to react to its temperature change. If you wanted, let's say, you needed a smaller thermal time constant for a specific purpose, and you wanted to see like what you could do to make it smaller, faster reaction time, you would change your mass and your surface area of your thermocouple to change that. So if you had a larger mass, that would mean a larger time constant. If your surface area was larger, then you'd have a smaller time constant, faster reaction time. So to talk about this, we need to look at the lump capacitance method, which is basically just let's say I have an object, and the temperature inside this object is just uniform, which means the heat conduction within the object is faster than the heat entering it, so we can just assume the heat inside is just uniform all around. And since we have heat entering, that also means we have a transient heat conduction, which just means it varies with time. This lump capacitance method, and its mathematics, it gave us a formula for our time constant tau, which you can see right there. I talked about how if we wanted a different time constant, we would change the mass. Well, we can see that right here with the rho v mass, and A, which is just our surface area. So these are the results from our experiment. This is just a temperature versus time graph. From here we can see we're going to have 4 different time constants. We have this one from being inserted into the hot water, this one being pulled out, this one inserted into the ice water, and this one being pulled out. Okay. That gives us some time constants. From what we can notice here, from what we can see here, our time constants are going to be very different from insertion and removal. When you put the thermocouple inside in the water, you have a lot smaller time constant than when you pull it out. And you have to ask yourself, why is this different? Well, the main difference here is water versus air. Water has higher density, higher heat capacity, higher thermal conductivity, which just means water is going to conduct heat faster than air will. So we can notice this, like when you turn an oven on, 300 degrees, you can stick your hand inside and fine. You can't stick your hand into 300-degree water, so you're going to get burned instantly. You know, that kind of thing. Yeah. So something this played a part in when we did our experiment was when we would take the thermocouple out, we would always wipe it off. That was just so our thermocouple, where the sensor was at the very tip, where they're welded together, the 2 wires, just so there would be no water on that, so it would have some direct contact with air. Because the water, yeah, it's very hot when it's in there, but as soon as you take it out, it's a little bit of water. The air, since its thermal conductivity is very high, it's gonna get rid of that heat really quick, and it's just gonna make gonna make our thermocouple have incorrect results. So that's pretty much my presentation. Thanks. Any questions?